Dear students, in this video we will discuss about what is tunnel diode. Tunnel diode is highly doped semiconductor device used for low voltage and high frequency switching applications. Work on the principle of tunneling effect. So here you can see that it's the sample of tunnel diode. Here it is an anode, it is the p-type material, and this one is the cathode, this made up of n-type material. So the tunneling diode is basically a p-n junction device. It's a p-n junction, p-type material act as an anode and n-type material act as a cathode. So here you can see that this is the tunnel diode, and the tunnel diode is basically a p-n junction device. So it's a p-n junction diode with heavily doped p-type region and n-type region. These are both are the p-type and n-type semiconductors. The tunnel diode is a is one which is heavily doped as the normal diode, therefore it has a large number of the carrier as a hole and electron. So the most of the carrier not used in the initial recombination in forming the depletion layers. So the depletion layer here is the very thin as compared to the normal diode. The function of the tunnel diode depends on the tunneling effect. So in the normal diode, the width of the depletion layer is very large, so it opposes the flow of the current between the n-type and the p-type semiconductors. So in the normal diode, to overcome the barrier, this depletion layer is the potential of this depletion layer is also called as the barrier potential. So to overcome this barrier potential, we need to apply the higher voltage, which is sufficient to overcome the potential barrier to start the current. So unlike the normal diode, this one is the tunnel diode, and it is different from the normal diode in the sense that by applying the small voltage, it is enough to start the flow of the current in the tunnel diode. So it's basically work on the principle of the tunneling. So first we need to understand the tunneling effect. So what is the concept of tunneling? So to understand the concept of tunneling, here first consider the depletion region. The depletion layer in the p-n junction diode is made up of the positive and the negative charges, positive and negative ions. These as initially when electron move to the p-type regions and the hole move from p to n-type regions. So here they create a depletion layers. So this during this initial recombination process, this depletion layer forms. So these are the oppositely charged ion. So there exists a built-in potential or electric field this in this depletion region. So here is the built-in potential or electric field within this depletion region. So the electric field in the depletion region exert a force in the direction which is opposite to the applied electric field. So here we will discuss the concept of tunneling by considering the flow of current through both normal diode and then through the tunnel diode, and we will differentiate between the two types of diode. So this is an ordinary p-n junction diode. Here we need to consider an important thing is that is the band, valence band and the conduction bands. So the valence band and conduction band of n-type semiconductors are lower in energy, slightly lower in energy than the conduction band and the valence band of p-type semiconductors. Here you can see that the valence, this is the valence band of n-type material and conduction band of n-type material, and this one is the conduction band of p-type material. So the conduction band of n-type material is lower in energy than the p-type material, and in the same way this is the valence band of n-type material and this one is the valence band of p-type material. So the valence band is also lower in energy of n-type material is lower in energy than the valence band of p-type material. So here you can see that, and so these are lower energy, there is a difference in energy. So this difference in energy between the conduction band and the valence band of p-type and n-type energy level is due to the difference in the dopant atom, that can be the donor or acceptor atom, which was used to create an n-type and p-type semiconductor. So this difference in energy, here it creates a potential barrier. Here it creates a barrier. So in order to pass the electron from conduction band of n-type material to the valence band of p-type material, they need to overcome this barrier. So here you can see that this barrier acts like this depletion barrier correspond to this depletion layer. So this depletion layer acts as a potential barrier. Here we can realize the potential barrier like this one. So this is the potential barrier. So electrons are here in the n-type regions and there is the p-type region. So for the electron with the energy less than barrier potential, this less than this barrier height cannot pass over the barrier. So the electron with energy greater than this, the potential of depletion layer are greater than barrier potential, can only with the energy greater than this barrier height will, this is the height of the barrier. So to overcome this barrier, electron of n-type regions, these needs the energy more than the barrier height. So we can say that, so when a forward biased voltage is applied across this tunnel diode, this ordinary diode, when the forward biased voltage is applied and type is connected to the negative terminal of the battery and p-type is connected with the positive terminal of the battery. So when the forward biased voltage is applied across this ordinary PN junction, so the width of depletion region decreases and the barrier height also decreases. However, the electron in n-type region cannot penetrate into the p-type regions. So if the applied voltage is greater than the built-in voltage of this depletion region, then electron from n side can overcome the opposite force of this depletion region. So they can enter into the p-type region. So it's work only when the applied voltage is greater than greater than the inbuilt potential of this depletion region, which act as a potential barrier. So here it is the tunnel diode. And tunnel diode, the situation is a bit different than the ordinary normal diode. Here you can see this one is the valence band and the conduction band of n-type material, and these are the valence band and the conduction band of p-type material. So again here the conduction band and the valence band in the n-type material are lower in energy than the valence band and the conduction band of p-type material. So all this energy difference in the level is greater than the normal diode, as we have discussed before. So this energy difference in the is greater than normal diode. Why it is greater than the normal diode? It is because of dopant atom. So here the tunnel diode is heavily doped. So here there are large number of majority carriers and a large number of the carriers are available. So it create a large difference in the energy level than normal diode. So here you can see that here the conduction, this due to this large energy difference, the conduction band of n-type region almost overlap with the valence band of p-type region. So due to this overlapping of conduction band of p-type region and the valence band of the p-type region, so the electron from conduction band of n-type can directly penetrate from conduction band of n-type region to the valence band of p-type region. So it means that here the width of depletion layer is very small. So as the tunnel diode, the width is very small and it is almost in the size of nanometer. So its width of depletion layer is in the size of nanometers. So here, so in the tunnel diode, the small voltage less than the width of this depletion layer is enough to produce the current in the circuit, because the electron can directly tunnel from n-type region to p-type region. Here you can see the physical visualization of the potential barrier. Here you can see that width of this barrier is very small, so the electron in the n-type region, instead of passing over the barrier, can directly tunnel through the barrier from n-type region to the p-type region. So this is called as a tunnel diode, and it can be used in the various electronic applications. So now we will discuss how tunnel diode works. So there are different steps. Step 1 is, in the step 1 we will consider unbiased tunnel diode. In the second step we will see that what happens to the tunnel diode when a small voltage is applied to the tunnel diode. Step 3 is the applied voltage is slightly increased. In step 4 we will further increase the applied voltage. And in step 5, what happened to the tunnel diode or tunnel current when applied voltage is largely increased. So now we will discuss all steps one by one. So first we consider unbiased tunnel diode. So here it is the unbiased tunnel diode. So here you can see that when no current passes, here in this case the no current passes through the tunnel diode. Why? Because initially we know that in the case of tunnel diode, the conduction band of n-type region and the valence band of p-type region almost overlap each other, and width of depletion layer is also very small. So when temperature increases and some of the electron from the conduction band of n-type region tunnel through this potential barrier and enter into the p-type region. In the same way, the hole crosses the barrier and enter into the p-type region. But overall, the net tunnel current will remain zero because of the equal number of charge carrier transferred from one region to another region. Equal number of hole and electron passes through the tunnel. So overall, there will be no forward current in the unbiased tunnel diode when a small voltage is applied to the tunnel diode. So here you can see that when a small voltage is applied to the tunnel diode, here is a small tunnel current. Why there is a small tunnel current? Although we have applied small tunnel voltage, this voltage is less than less than the barrier voltage or inbuilt voltage of depletion layer. Although it is the less than the barrier voltage or depletion layer inbuilt voltage, but still it can start a small tunnel current. Why it is possible? Because we know that the width of depletion layer is very small and conduction band and the valence band of p-type material and conduction band of n-type material overlap each other. So with the small tunnel current is when we apply a small current, small forward current, then the sum of electron directly tunnel through the potential barrier and enter into the p-type material, thus creating a small current. So we can say that the tunnel diode can start the current with a small applied voltage. When applied voltage is slightly increased, when we slightly increase the applied voltage, then tunnel current reaches at its maximum value, because now the conduction band and the valence conduction band of n-type material and valence band of p-type material, here you can see that they become exactly overlap each other, or they have the same now they have the same energy, they are at the same energy level. That's why large number of the electron from conduction band of n-type material uh, cross the barrier, cross this tunnel and enter into the p-type material. So it will increase the current, and the current reaches at its maximum point when we applied when applied voltage is slightly increased. So here you can see that when applied voltage is further increased, when we further increase applied voltage, here the tunnel current, instead of increasing, it start decreasing. So tunnel current start decreases when applied voltage is further decreased. Why it start decreasing instead of increasing? Here you can see that here the conduction band of n-type semiconductor and valence band of some n-type p-type semiconductors. Here now there is a small misalignment in, and they, although they are still overlap with each other, but there is the small misalignment when we further increase the applied voltage. So still they overlap, so some of the electron from n-type of the conduction band of n-type region passes through the tunnel and enter into the valence band of p-type region. So the tunnel current at this point, instead of further increasing, the tunnel current start decreasing with the increase in voltage. So next, when applied voltage is largely increased. When applied voltage is largely increased, now here you can see that tunnel current, zero tunnel current and maximum forward current. Why now there is the zero tunnel current? Zero tunnel current is that now the conduction band and valence band of n-type semiconductors are largely misaligned than p-type uh, conduction and valence band of p-type semiconductors. Now there is the large misalignment between the conduction and valence band of p-type and n-type semiconductor. So uh, at this point, this tunnel diode behave as a normal diode. So when we apply the voltage larger than this barrier potential or inbuilt layer potential, then it will start the forward current in the circuit. So at this point it is in the negative resistance region. So this negative resistance region is very important for the different applications of tunnel diode. So what are the advantages of tunnel diode? It has a long life. These are used in the high speed operation, and these are the low noise and low power consumption. And what are the disadvantages of tunnel diode? So the first disadvantage of tunnel diode is that tunnel diode cannot be fabricated in a large number. Secondly, being a two-terminal device, input and output outputs are not isolated from each other. Now, what are the applications of tunnel diode? Tunnel diode are used as a logic memory storage devices. Tunnel diode are used in relaxation oscillator circuits. Tunnel diode is used as an ultra high speed switching applications. And tunnel diode are used in the FM receiver. These are the important applications of tunnel diode. Thanks for watching. For more videos, please subscribe our channel.